Hello everyone, welcome to my PlayStation. My name is Xiang and I'm from Mississippi State University. My PlayStation today is about ethane aromatization and I will discuss the influence of nickel-gallium metal function on the early stage reactivity and stability. The background about ethane aromatization is certainly related to the current shale gas revolution. According to EIA, the total reservation of natural gas in US is up to 400 trillion cubic feet. Consequently, the production of natural gas or natural gas liquid soared during the past decade. For example, the natural gas liquid alone, the production is up to 5 million barrels per day. As a result, the global, or especially the US, energy structure and chemical industry is reshaping from crude oil to natural gas and natural gas liquid as the major resources. With such feedstock shifting, it is not surprising that the landscape of chemical industry is also changed. For example, the cost of ethylene has dropped, but the price of the heavier products such as benzene, toluene, and xylene have increased. As a result, we require the development of the on-purpose catalytic technique to selectively convert the natural gas to liquid or slow CC bond formation or slow dehydrogenation, right, to the petrochemical products. Talking about the aromatization, we know the natural gas liquid compounds, or especially the C3 to C5 compounds, can be converted to the aromatic through the industrial process known as circular process, aeroforming, or aromax. But a similar process for ethane conversion is waiting to be developed. And this is because ethane is more stable than propane and higher lactic alkanes. So catalytic ethane conversion requires a higher reaction temperature or a more stable catalyst. And if we use a higher temperature, so the catalyst is deactivated very significantly due to cooking. So here I show the reaction pathway of ethane aromatization according to literature as well as our recent study based on the transition kinetic. And the whole reaction process requires both metal function and acid function. The metal function is catalyze the dehydrogenation, for example, start from ethane to ethylene, and in the meantime, it also catalyzes the hydrolysis and forming byproducts methane. And the acid function normally is responsible for the oligomerization. So start from ethylene, we produce long-chain olefins. And since we require such a bifunctional catalyst, if we go to literature, here I list a number of patents which shows that different metal modified cesium-5 catalyst is active in ethane aromatization. And as we can see here, the metal function is namely more important. And we found here the metal function including zinc, gallium, and platinum is most investigated. And besides this, other metals such as molybdenum, iron, nickel, uranium, and cobalt has also been reported to be active. And as I said here, the metal function is the key because the acid function is from cesium-5, which is normally known to everybody, but the metal function is the key to tune the performance. And in this presentation, we will discuss the influence of nickel, gallium, and nickel gallium. And the reason why we started this because nickel gallium is kind of intermetallic alloy, and it shows already very unique performance in ethane dehydrogenation. And our recent study also shows that when we have the nickel gallium intermetallic supported on cesium-5, it also shows very good performance in ethane aromatization. So we claim we have the nickel gallium intermetallic alloy. So here I show some characterization show we indeed have such kind of alloy. So the first characterization I show here is the STM-EDS mapping. And as we can see here, the gallium and nickel show a very, very unique or very, very homogeneous distribution with each other. and which means when we have nickel somewhere, we also have the gallium. The nickel and gallium have very, very close proximity. And this is one hint for the formation of alloy. Okay, so the direct evidence about the formation of nickel-gallium alloy is from XRD. As we can see, from the nickel-gallium bimetallic catalyst, a new peak at 43.5 is appeared. And this peak, according to literature, is nickel 3 gallium 1 intermetallic alloy. And such peak was observed when we have the pure nickel or pure gallium. So this is a very direct evidence about the formation of nickel-gallium alloy. We also have other evidence about the nickel-gallium alloy from XPS. For example, from XPS, we can see when we have the monometallic gallium, or when we have the gallium which is very low, we have all of the gallium as the gallium O+, so it's gallium 3+ oxidation state. So it is oxide, it's not metallic, intermetallic alloy. But we can see with the increase of the gallium content, the gallium 0 peak here, it's increased. Right? So when we have the gallium 0, it's metallic state, it is another hint about the formation of intermetallic alloy. And it's the same from the nickel spectrum. Right? From the nickel, when we have the pure nickel catalyst, we can see the nickel is 2+, which means nickel is exchanged to the zeolite and it forms the nickel 2+ cation. But if we have the gallium, when we have the gallium, the catalyst or the nickel species was reduced. It forming nickel 0, right? It's metallic nickel. And again, if we compare this nickel 0 and with this gallium 0, we again assume that we have some nickel-gallium intermetallic alloy. So when we have the nickel-gallium intermetallic alloy, we can also show how it was produced or at which temperature it can be produced from the TPR. So here I show this TPR profile for the modern metallic nickel and also show the nickel and gallium and also the gallium monometallic. And we can see here for the monometallic nickel, it was reduced at 367 degrees C. But if we have nickel gallium, and the reduction peak or an additional reduction peak was at 610. Right, so with this information, then in all our preparation of the catalyst, we use a reduction temperature of about 650 degrees C. So in this case, we can ensure all the sample was reduced to metallic and forming the intermetallic alloy. So now we look at what is the influence of nickel-gallium or nickel-gallium species on the acidity. Right, so the left panel shows the ammonia TPD original file, and we can see from the TPD, the pure cesium 5 certainly shows more strong acid, right, at the peak of about 450 degrees C. And with the presence of nickel and gallium, this strong peak decreased, right? It's slightly decreased. And in order to make it clear, I plot here the acidity deviation. Right? So we take the TPD profile of different sample and minus the original file of the cesium 5, and we got this profile. And as we can see, a new Lewis acid site is appeared with a nickel 1 gallium 1 sample. Right? When we have nickel gallium, which is 1:1 ratio, this new Lewis acid peak is appeared. And it's the same for other nickel gallium bimetallic catalysts. And additionally, the strong peak or strong acid peak at 450 or 500 is decreased. It's slowly decreased with the presence of nickel and gallium. But what is interesting here is when we have the nickel gallium 1:1 ratio, the lowest decrease in the strong acid, right? It's very close to the monometallic gallium, right? We have the red, which is monometallic gallium. And when we have nickel gallium 1:1, it's pretty close to the monometallic. And that's also, I will discuss later how ensure we have a good performance. So now let's look into the results. First, I show the early stage behavior, and I talked in the title, we're interested in this early stage reactivity. And it's very interesting here, when we have the nickel on session 5 in the monometallic catalyst, a very, very long induction period, up to 10 minutes, was observed. And during this induction period, as we can see, we produce only missing. Right? So this is a missing signal, the black one. And the ethane conversion is about 100%. Right? So the red one, which is ethane. And during the first 3 minutes, ethane was totally disappeared, which means ethane was 100% converted to missing during this induction period. And later on, slowly, the formation of missing decreased. And of course, the ethane signal increased, right? Decreased the conversion, and of course, also decreased missing formation. And until 10 minutes, then we found the formation of benzene, the green one, which is benzene. And we also found the formation of ethylene, the blue one. And we also found the formation of toluene. So all these aromatics was produced with a delay up to 10 minutes, and which means we have a very, very significant reconstruction during this early stage. And quite interesting, when we investigate the gallium sample and nickel gallium sample, such a long induction period was disappeared. And for gallium sample, as we can see, the delay for the toluene is only about a minute. And the delay for benzene is only half minutes. And for ethylene, there's almost no delay. So this is the behavior of the early stage on the gallium sample. And now, if we look into nickel gallium sample, its behavior more likely the gallium sample rather than nickel sample, right? So the delay of the toluene is about 2 minutes, and delay of ethylene, there's almost no delay, and it's the same for benzene, almost no delay here. And we found we have a small short peak here, which can be originated from the different active site inside the catalyst. Okay, now if after looking into the early stage, here I'll show the time on stream behavior up to 2 hours or more than 2 hours here for different samples. As we can see, for the nickel samples, the conversion initially was 100%, and it is sharply decreased to about 30%, and then it's deactivated very, very fast, or much faster than other sample. And the gallium sample is more stable, much more stable than the other two samples. And we can see the most interesting is the nickel gallium sample. It is more active than gallium, but it is also very similar stability like the gallium. And in terms of selectivity here, as we can see, the nickel gallium sample show very, very similar, or the same, we can say, selectivity, BTX selectivity with the gallium sample, but the monometallic nickel, the selectivity is much lower, and it is deactivated very, very fast. And here in this panel, I show the rate of BTX, so the total rate of formation of aromatics. And as we can see here, the nickel sample deactivates very fast, and the gallium sample is the more stable, and the nickel gallium sample is higher rate than the gallium, but it's also pretty similar stability like the gallium. So now we show what is the deactivation kinetic model, because the deactivation is very common in the aromatization, and if we can develop a model for deactivation, it will be very helpful to understand what is the mechanism. So we start with the general power law model for deactivation. And here we show this negative dA of dt equals to Ka alpha power of n. So this A is calculated from the rate at any time over the rate at the initial state, which is the rate without deactivation. So for this deactivation model, we can analyze based on the first order deactivation and also second order deactivation. So with the first order, we can move forward based on the mathematics, and we can model it and fit in the process. And the same for second order. And we did this model, and we found actually after modification with time here, t with alpha, then we found a very, very good fitting. So here I show the results. the BTX, if we fit this model with the second order, here I show only the second order as example, it shows very good linear relation for this natural log 1 minus a of a and with natural log t. And we can then calculate the deactivation constant, right? So this constant is much higher of the nickel and much lower of the nickel gallium and even much smaller of the gallium. So we have this decrease of the red constant of deactivation from nickel to gallium. And then we refitting our model and compare with the original data, and we found actually it is fitting very, very well, and only very slightly deviation at the early stage. So here we show that the gallium is most stable, and the nickel gallium is higher activity again, but it is more stable than nickel and less stable than the gallium. So here's the conclusion. We conclude that the early stage behavior depends highly on the metal function, right? So the formation of BTX on the nickel 75 shows significantly, which is almost absent of the nickel gallium catalyst. The activation of the catalyst follows the modified second order power law, and the activation constant highly depend on also metal function and decrease following the order of nickel larger than nickel gallium and larger than gallium. So finally, I would like to acknowledge my student, Sivaj, so he did most of work. And I also would like to acknowledge my collaborators and especially the funding from the nice American research. Thank you.